right, so we want to do section 7.2, exercise 58. And let me make sure that was 58 here. I think it was 58. Yes, 58. And this is where we want to take a sphere and we want to drill out the center like that and get rid of that. And so that will make a ring if we turn it on its side and look down the hole. You know, we would see something like that, spherical sort of ring. Okay. Now, so what we're told is this has a radius of 6. Okay, so, you know, we have something like this where that's a radius of 6, which means this curve is x squared plus y squared, equals 6. And so if I write the top half of that as a function, that's y equal the square root of 6 minus x squared. And we can think of a sphere as taking this little half circle and rotating it around the x-axis here. And so that would make a sphere, and so we would simply rotate it that way. Okay, now what they want us to do is drill this thing out, drill part of it out at some radius r, like that. And what we have left up here, when we rotate it around, we want that to be half the volume of the sphere. So the volume of the sphere, well, that's 4/3 pi r cubed. Okay, so they said the 6 was big R here. So that's 4/3 pi times 6 cubed. Now I could reduce that a little bit by taking one of the 6's over the 3, I guess, and so I could make that 8 pi times 6 squared. And you know, I could multiply 8 times 36 and get whatever that is. Let's see, 8 times 36. Well, 8 times 30 is 240. 8 times 6 is 48, so it looks like 288 pi. That's the volume of the sphere. Okay, now when we rotate this thing, I guess we have a washer method sort of idea, right? We have the outside minus the inside. And in this case, it might be a little easier to just go ahead and write that that way. So, you know, I want my big R squared, except they called that big R. Why'd they do that? I don't know. So my outside, I'll call that rho, and my inside radius, I'll call that the little r. And so you know, we want the integral from, well, some a to some b here. We don't know what those are yet. They are not 6, because when I cut this off and that comes straight down, that's going to be short of the end of the sphere. So for right now, I'm just going to call it, well, actually I could call it minus a and a. All right, so I could call that minus a, and that should be a, because it should be symmetric. And I need my pi, and I need my rho squared, the outside minus the inside, and then my dx. Okay, so I need to get those two things. Well, the inside is just r squared, and that's all I know. Gosh, now that I think about it, did I mention what we have to do? Right, we have to drill this out so that we leave half the volume. So we want to drill out half the volume, keep half the volume. Not sure why I'm not sure I said that, in the problem description. And so in that way, our volume of the sphere over 2 is 144 pi. Okay, and this is much like what example 5 on page 451. So again, I should probably add that up here. This is similar to example 5 on page 451. And so we're attacking it pretty much that same way. I drew it like they did. And so at this point, we just need to figure out what rho is, looking here. Well, let me draw it again. Okay, so that outside is this thing, and we know that that is just y equal the square root of 6 squared. Oh, did I say 6 squared or 6? Oh, no, 6. Sorry. Wait a minute. Yeah, the radius is 6. Sorry about that. 36, 36. Right? So these are all fine, 6 cubed and so forth. And 6 squared. So y equals the square root of 36 minus x squared. So sorry about that. It's tough to talk and write this stuff down, as you're doing it. I don't, I sort of apologize, but I don't really apologize, again, because, it points out that, well, for one, multitasking is hard. And the other is, sure, I can make little mistakes that, I know what the answer is. I know it's r squared. X squared plus y squared is r squared. I know that. But it doesn't mean I always write it down correctly. So, and again, as you think through things, hopefully you catch such errors. And okay, so we have this 36 minus x squared. So I'll try to keep that right now. And so we want that value squared. So that's just 36 minus x squared without the square root. So now at this point, we're able to write this as pi minus a to a of 36 minus x squared and then minus r squared dx. And so we have that. Now what we have to do is figure out, okay, if this is r, if that height is r, what's x here? What's the minus a and what's the a? Well, we have that, x squared plus y squared is equal to 36. Notice I wrote it correctly that time. So if y is r, then I have x squared plus r squared, little r squared, has to be 36. And so x squared is equal to 36 minus r squared. And so x is the square root of 36 minus r squared. And so that is our a. And so I have plus and minus that. So this is pi, the integral of minus square root of 36 minus r squared, up to plus square root of 36 minus r squared. 36, and I'm going to write this as 36 minus r squared, since that's all a constant, minus x squared dx. So then this is, these antiderivatives are easy enough. So I have pi times 36 minus r squared, all times x, and then minus x cubed over 3. Okay, and that goes from minus the square root of 36 minus r squared to plus the square root of 36 minus r squared. And okay, now plugging those in, actually if I square that, that's really nice. So this has an x, that has an x. I'm going to factor all that out, the x out. And so what I have then is this is pi times x. Okay, well, what's x? Oh, well, actually, I should do it like this. So pi times, and I'm going to factor out the x, and then times 36 minus r squared, and then minus x squared over 3, like that. And do that from minus the square root of 36 minus r squared up to the square root of 36 minus r squared. Now in this way, it might have been easier to leave it as a, a minus a and an a, and then take care of it when I was all done, but we'll see. Okay, so here's pi, and I need to put both of those things in there. So I have the positive square root of 36 minus r squared, all times 36 minus r squared, minus, now when I square that, I just get 36 minus r squared over 3. And then minus, now it's going to be minus x. So x is negative 36 minus r squared. So this becomes plus square root of 36 minus r squared. And then times exactly what we had in there before. So 36 minus r squared minus 36 minus r squared over 3. So as I look at this, this is a pi times, well, both terms have the, oops, I'm not sure what I just did, but both terms are the same thing. So there's just two of those. So I have 2 times the square root of 36 minus r squared, and then times this thing in here. Now that's 2/3 of 36 minus r squared, because I had 36 minus r squared and I'm subtracting 1/3 of it. So that's 2/3 of 36 minus r squared. And so, well, looking at all the constants, I'm going to keep the 36 minus r squared by itself. So I'm going to write this as 4 pi over 3, and then times 36 minus r squared to the 3/2. Okay, so I just took to the 1/2 there and took to the full power there, added those powers, it's 3/2. Now the question is, does this look okay? And I can check that because remember, I know the volume of the sphere up here, right? The volume of the sphere should be 4/3 pi times 6 cubed. And on the other hand, if I let little r here go all the way up to the top, I should get a volume of 0. Okay, so if little r equals 6, so all the way to the top, notice that implies I get a volume of 0. And if I let little r equal 0, that implies I get 4/3 pi times 36 to the 3/2. But that is 4/3 pi times 6 cubed. So at least at r equals 6 and r equals 0, I am correct. And so now it is just a matter of solving this equation for r when we have that volume equal half the volume of the sphere. So 144 pi. So what we need is for 4/3 pi times 36 minus r squared to the 3/2 to equal 144 pi. Okay, well, divide both sides by pi. We've got that. Multiply through by 3/4, and we have 36 minus r squared to the 3/2. Well, 144 divided by 4 is what? 36? Is that right? Yes, 36. And so multiplied by 3, we have 3 times 36, which is 108. So we get that. Now I need to take 2/3 of everything, 2/3 power of everything. So then we get 36 minus r squared equals 108 to the 2/3. Now the question is, can I do anything with that? Well, I had 36 times 3, right? So my factors are 3 times 3 times 3 times 4. And now I'm going to square that. So I'm going to get another 3 times 3 times 3 times 4. And I want to take the cube root of that. And it looks like I get 36 minus r squared is equal to, again, notice this is, I get 3 to the 6th power and 4 squared, right? So when I take the cube root of that, so I squared the 108, okay, that was doing that. Here I squared the 108, the 3 times 36, and then that, looking at the factors, that's 3 to the 6th. Well, the cube root then, cube root of 3 to the 6th is 3 squared, so I get 9, but the cube root of 4 squared is just 4 to the 2/3. Well, actually, I can do better than that, I guess, because the 4, right, that's 2 times 2, and then another 2 times 2. So there's a cube root part of that. So I can have this be 36 minus r squared, and that'll be the cube root of 2 times 2 times 2, which is just 2, so I'll get 18. And times the cube root of 2. So I could write that as a 3 there and a 2 there, 2 to the 1/3. Okay, so, because again, I should have had this as 2 cubed times 2, right? And so I get that. So now that means what? R squared is equal to 36 minus 18 times the cube root of 2. And so r is equal to the square root of 36 minus 18 times the cube root of 2. Wow. Okay. So that appears to be our answer. Now, what the heck is that number? let's just look to see if that number seems reasonable. Bring up Desmos. And so what we did was we took the square root of, now I got to go back, the square root of 36 and then 18 cube root of 2. So 36, well, get back inside there. So 36 minus 18 times the cube root of 2. So I guess I'll have to do 2, times 2, and then to the 1/3. 1 divided by 3. And that says it should be 3.64. And, right, is that, yeah, if I have that correct? Yep, cube root, okay. So it says R should be a little bigger than 3. And so, well, you know what? I'm not sure I believe that. And so, probably an error somewhere. And let's see if I can spot that real quick here. So I'm pretty happy with all that stuff. I don't know. All right, well, I paused for a little bit so I could put in this integral and all that, and experiment a little bit. And wow, you know, this is a case where I thought I was wrong, but I was mistaken. And because what we see is, you know, 144 pi is 452. And if I do my integral here, s equal 365, and I used s instead of r because, again, Desmos, you start using r for things, it can get a little confused. So I used s, and, you know, there's 452 when I'm at 3.65, and we got an answer of 3.649. So there it just shows my intuition was just way off, is that hole is bigger than half the radius. Go figure. So, you know, so I checked it back. I'm very sure that that is correct. And so it just became a matter of, did I really believe I'd done all these calculations correctly? And when I got that answer of about, you know, 3.65, I thought, no, you know, because that would say that you have to drill out a hole bigger than half the radius, right? You know, so as you go here, in order to get half the material. So this cylinder, you know, I was expecting that cylinder sort of had a bigger volume in a way, you know, relative to this radius that we used here, little r. I was wrong. Okay, so in that way, I was wrong. Okay, I was expecting a different answer. I thought the answer might be less than 3. Definitely not. It's 3.65. And there you go, a very long derivation. These problems can be very long. Now, you know, but on the other hand, once I set it up, you know, it doesn't take much to get Desmos to give me an answer. Now here I had to, I put in, you know, if I was going to do this numerically, right, what I had to do was experiment with that s. So I knew what the answer needed to be down here at 144 pi. I plugged in the integral with a slider, so that variable s, and I moved it around till I got around the 452 that I needed, and that number was about 3.65, and which is what we got doing it the other way. And so you know, you can do it numerically with something like Desmos, but it you know, it is just that. It's a guess. Whereas back here, well, once I decided with my checking it on Desmos that I got the right answer, here, here we've got a right answer as opposed to something close. Okay, so there we go, number 58.